So here we're going to look at the second half of chapter 3. We're going to look at 3.4 through 3.6. I'm going to mention stuff about 3.5, but we're really not going to cover it in the context of this class. It's kind of cool because we start graphing like linear equations in 3 variables. So here's where we start to add that dimension of depth versus we've always done like 2-dimensional, just Cartesian plane stuff. So it's definitely interesting, but we're just not going to do that much with it. So we're basically going to leave it as is. The first thing we're going to start out with is linear programming. Now, linear programming is super similar to what we just finished off doing, where we have systems of linear inequalities. So this is basically like I have a system of linear inequalities here, and then I'm saying, okay, we'll find the max and the min of this system. Now, if this system is unbounded, so say for example, I didn't have like this restriction here, it just kind of went up to infinity like this, that would be an unbounded system. So sometimes we can have infinite maxes and mins, but in terms of most of these that we deal with, we'll be dealing with a finite minimum and maximum. So what we're going to do is we're going to take this one here as our example. Now I'm going to just highlight our objective function, which is referred to as our cost function. Okay, this is how I determine my min and my max. So when I want to know what's my minimum and what's my maximum for the given system, it's going to be based off of this objective function. Now in terms of figuring out what that system is, I have this first thing here in orange, I have another thing here in green, and then I have a third thing here in blue. So when I'm doing this problem, each of these is going to be a constraint. So the first one, x is greater than or equals 0. Well, x equals 0 is going to have a vertical line right at 0 here, and then I'm going to be to the right. And it's going to be a solid line here because it's greater than or equal to. And now I'm going to shade this region, and I'm just going to leave it like that. So my first one is done. The next one here I'm going to do in green. So y is greater than or equal to 0. Here's my horizontal line. I'm going to be shading above this thing. And again, it is a bold line because it's greater than or equal to. For the last one here, I might want to change the way it looks a little bit. So maybe I want to subtract x off both sides. So if I subtract x off, I get y is less than or equal to negative x plus 5. So let me just erase that for my own OCD. And now as I look at this, I'm saying, okay, well, I start at 5, 1, 2, 3, 4, 5, put a little point there. My slope is negative 1. If m equals negative 1, this means I can do one of two things. I can go down 1, right 1, or I could go up 1, left 1. These are both equivalent. So when I'm looking at this, I'm going to go down 1, right 1, down 1, right 1, down 1, right 1, one more, and the last one here. Call it good. This is going to come down through just like that, and I'm going to be shading below this thing. So the reason I'm shading below is because I have y is less than or equal to. It's a solid line rather than a dotted line because it's less than or equal to. So now I want to find the common bounded region. So I'm going to pick a dark purple here. From this point, all this stuff in here where it's green, orange, and blue, okay, it's all three of these things, is going to be my shaded bounded region. So now as I'm looking at this, there's really 3 points that are going to define this region. Now, if it was something like this, a quadrilateral, then this thing is going to have 4 points that I'm going to want to test. This one only has 3. I'm going to label them A, B, and C. So these are going to be kind of the outliers of my system here. So I get my points A, B, and C. I'm going to label the points. I find this is super helpful for most people. So A is at 0, 5. B is at 5, 0. C is at 0, 0. Now in terms of plugging these things in, I'm going to take it and plug it into my cost function. My cost function, or my objective function, is 2x plus 3y. So if I plug this in, I'm saying 2 times 0 plus 3 times 5 gives me 15. Then for my b value, I'm going to say, okay, it's going to be 2 times 5 plus 3 times 0. Again, if it is 0, you don't really need to plug it in, but I'm just writing it out for clarity's sake here. So here now I'm going to be left with 10. And the last one here I got double zeros. Too bad there's not another one. We could do James Bond with a 7 at the end. But here I'm just looking at 0, and I've circled this, and I've circled the 15. Now I'm looking at this. This is my maximum. Looking at this, this is my minimum. So as I'm looking at my objective cost function here, my minimum is 0, my maximum is 15. So again, it's always just based off of whatever these points are. There's no point that's going to be along this thing that's going to be able to match those mins and maxes, relative, depending on where they are. I'm going to talk about the graphing very, very, very briefly, and then we're just going to move on. So again, we're not spending a ton of time here. I just want to at least show you what it's all about. So here we're looking at a graph. This is my x coordinate here. So this is the one that we kind of think of as coming out towards us. So this is towards our faces. This would be away towards, wherever we're pointing. So we've got this slide here. We have y, which goes left, right, and then we have z, which goes vertically up, down. So in terms of defining something, we would say this thing kind of comes out 4 to me, and then it also goes down to the ground, 4 down in there, and then it goes kind of 3 off to the right over here. And it defines this bounded region right here. So when we're trying to do problems like this, basically it's just adding in another dimension. We can solve using individual variables, but again, we're not doing a ton with this, so I'm going to kind of leave it at that, and we're good there. We are going to do a lot with solving our systems of linear equations here in 3 variables. So this may seem a bit overwhelming at first. I promise that once we go through it a couple times, it's really not too bad. So the first thing I want to note here is that I have 3 equations. So I have this that I'm starting out with. Okay, this is my given information. So I have x minus 3y plus z is 22, 2x minus 2y minus z equals -9, and then x plus y plus 3z equals 24. When I look at this thing, I see, okay, 3 equations and 3 variables. I am able to solve that thing. Maybe it has infinite solutions, or maybe it has no solution. That's a possibility, but in terms of if there is a solution, I am able to solve it. So if I just gave you 2 equations with 3 variables, for example, we would not be able to solve. There's always one that's going to vary relative to another, so we don't actually pinpoint anything down. So for this one here, we're going to really take it one step at a time, and the first thing we want to do is just look at 2 of the equations. So I'm just going to take these 2 equations here. So when we're choosing which 2 equations we want to look at, all I have to make sure that I do is that I want to combine 2 sets of equations, so top and middle, and then I could do top and bottom, or I could do top and middle, middle, bottom. Okay, so I just want to make sure I'm combining all the combinations of equations available to me, and then when I'm doing that, I'm trying to eliminate the same variable. So I'm choosing which variable I want to get rid of. For simplicity's sake, I'm just going to get rid of x's. You can absolutely do it with y's. You can absolutely do it with z's. Z's is probably actually the easiest option. Maybe I'll switch to do with z's. Yeah, I'll do z's. So looking at this, I've got 2 3-variable equations, so I'm just going to rewrite these real quick here as x minus 3y plus z. Veinte dos there. We got 2x minus 2y minus z equals -9. So when I am setting this up, what I would like to happen is for my z's to cancel off. Now, do they cancel off as is right now without me modifying either of these equations? Yes, they do, which is pretty sweet. That's the least amount of work that I could possibly do. So if I were to take these 2 equations and just add them up, I have stuff on the left equals stuff on the right. Stuff on the left equals stuff on the right. So can I smash them together? Yeah, of course you can, right? We're balancing everything here. So in terms of what's going on here with these z's, they drop off. My 2x's, my x on top and x on bottom. I don't want to say 2x because it's 2x right here. But my x's add up to give me 3x. Here I have a -3y and a -2y to give me a -5y. My z's cancel off, so I'm not going to write anything here just for clarity's sake. You can write plus 0z if you want to, but I don't know why anybody wants to do that, except for the Wizard of Oz. Get it? And then we have 22 minus 9, which will give us 13 here. So now this is my first 2-variable equation. So I wanted to show you us doing this before I explain why I'm doing it. So the reason I'm doing this is that I can take multiple 3-variable equations, add them up to turn them into two variable equations by canceling off the same variable, and then from there I can cancel off just like we did before using either elimination or substitution. So in doing so, I now want to create another pair. I'll just do these two. If you wanted to do first and third, that'd be fine as well. I'm just going second and third. So I'm going to copy these down. That's 2x minus 2y minus z equals -9. I never use z's by choice because my z's look like 2's. Hopefully the little loop in the 2 is clear there for you. Apologize for my bad handwriting, but it's the best I can do on a graphic tablet. Oops, a little too much z action there. And we're going to do the same thing again. So keep in mind, this is my first and second equation. Now I'm using my second and third equation. So when I'm doing this, I want to cancel off my z's, okay? We cancel off z's here. We want to cancel off z's here. Now I can't just add these up because the z's don't immediately cancel off. So there's a little bit more work that I have to do to this thing. So in order to do that, what I would like is to turn this top part into a -3z. It's already -z, so what I'm going to do is multiply it by 3. So by multiplying the top equation by 3, it becomes, so again, 3 to everything. So now it's going to be 6x minus 6y minus 3z equals -27. I've squished myself into the corner here, but hopefully that's at least a little bit legible. So now from here, I'm going to copy down my original equation. So I'm actually going to take this and just paste it down below. A little crooked, but that's all right. Can even space it out a little bit here. There we go, it's a little bit nicer. So now I am dealing with these two equations right here, and I'm adding them up. Maybe I shouldn't have done that. I should just copy it down. That way it's not confusing. Don't be lazy, Mr. G. Being lazy is best done when you're more clever about it. So we should just take this and write it down again. So now we have this thing plus this thing. There we go. Alright, try that again. So now let's add these things up. What color have we not used? This purple. It's a pretty sweet color. So again, I'm adding these things up. So in doing so, I'm going to get 7x minus 5y. I could write plus 0z, but again, nobody does that except for the Wizard of Oz. And then here we have our 24 minus 27 will give us a -3. So now I have my second two variable equation, and this is very important. So now what I'm going to do is I'm going to take the two variable equations, this one, and I'm going to add them together using either combination or I could do substitution to solve for one of my variables. So in writing these two, I'm just going to jot it down below here. These do take up a lot of space, so just keep in mind, give yourself plenty of space for these. 3x minus 5, it's better to be slow and meticulous than to make any mistakes. I want to change one of these things such that one of my variables cancels off. 7 and 3 is going to be a little bit more work versus -5 and -5. All I have to do is hit one of these with a -1. So I'm going to just take the top one and hit it with a -1. And so now we have -3x plus 5y equals -13. And we have 7x minus 5y equals -3. From here, I'm going to add the things up. So I have -3 and 7 gives me 4x. Here, these are going to cancel off. And now I'm going to get equals -16. From here, I solve for my x value by dividing by 4, dividing by 4. So I get my, x equals -4. Now this is one of my answers, okay? So this thing is pretty important here. What do I do with this thing? Well, once I have one of my answers, I'm going to take it and plug it back into one of my two variable equations. Again, it really doesn't matter which one you plug it into, whether you want to plug into yellow or whether you want to plug it into the darker purple here. I'm going to go yellow just because, I don't know, it's on the left, so why not? So I'm going to say 3 times, now I'm going to fill in that value, minus 5y equals 13. Again, the value that we are filling in here is for our x equals -4. So in terms of evaluating this thing now, we have -12 minus 5y equals 13. I'm going to add my 12. So -5y equals 25. My final y value here is -5. Now that I know my x, and let's do a little double triple circle. So now that I know my x and my y, I'm going to go back and grab one of my original 3 problems. So looking at this, I'm going to say, okay, well, which one of these do we want? I don't know, and I don't care, so I'm just going to grab the first one. And I'm going to copy it down here for us. So now I want to take my, it's very, very small. Hopefully people can see that. I don't know, blow it up a little bit, but it's going to get super distorted. I don't know which is better, the small text or the distortion. So looking at this now, I'm going to plug in the variables that I do know. So I know x and I know y. So looking at this, we've used pretty much every color. Let's try the lime. Lime? What is this color? Yeah, lime. Nailed it. All right, so my x value I know is -4. Plug that value in. Minus 3 times my y value I know is -5. And then it's just plus z equals 22. So here I have -4 plus 15 plus z equals 22. -4 plus 15 gives me 11. So 11 plus z is 22. Last move here is to subtract 11 and subtract 11. So my z result is 11, and we're good to go. So that's how we solve our systems when we've got 3. So solving systems of linear equations with 3 variables, the first step is I want to get two variable equations. That's what I did here in orange, and that's what I did here in green. Okay, so the orange thing turned into yellow, the green thing turned into dark purple. Again, I want to try and eliminate one variable. I'm going to use either the first and second and the first and third equations, or I can do first and second and third equations. Now when I do this, again, choose a variable that's going to be easy. I could have done, x's, I could have done y's. The reason I chose z's is the least amount of work for me to do in terms of multiplying and matching these things up. So again, it's more of a skill set we build out as we do a few of these and get more experience. We're not going to do a ton of them going forward, so I wouldn't worry about it too much. But that's it. Oh, sorry. So I don't know. Yeah, I'll walk you all the way through it. So first we find our two variable equations, and then we say, okay, now use those two to get one of the variables. So once we solve for one of our variables, we plug it back in, solve for our second variable, and then we take both of those, plug them in to solve for our third variable. That's start to finish with this, and that wraps up chapter 3 for us.